Good afternoon. I'm Anusha. I'm going to introduce zSense. This is a collaborative work with Roshan, Nipuna, and Suranga, who are my colleagues at Augmented Human Lab in Singapore University of Technology and Design. zSense is a gesture recognition system that we designed for smart wearables. Smart wearables are usually always available input, and they are usually, again, very small. Not only the device itself, but also the interaction space. That's why we need something like gestures, so we can increase the expressivity of human towards the device itself. So tracking gestures is nothing new. We have seen really amazing work even within this session itself. There are ways to track gestures using depth cameras, time of flight sensors, and just using simple IR emitters and sensors. Also wearing other trackers. But when we are designing for wearables, again we have to consider about, at least in our case, we consider three main issues. First is the size. When it comes to wearables, size really does matter. So not only the size of the device, again the interaction space. And also these devices usually have limited battery power. So energy is another concern. And again, these devices are quite small and they have limited processing power as well. So we cannot do a lot of calculations, floating point and stuff. So we thought, could we make a simpler gesture tracking system just for these small wearable devices? The conventional way of, especially the camera-based way, is sampling the space linear. A camera is essentially an array of sensors that map the space to each individual sensors within the camera. And in the post-processing, most of this data is discarded. So we thought, can we reduce the number of sensors? As a matter of fact, can we just use one sensor to track gestures? How many gestures we can track with one sensor? And if we add two more to make it 3 sensors, can we increase the number of gestures we can track? This is exactly what we did with zSense. zSense is a spatially efficient and non-focused gesture sensing system that consumes very little energy and use very little processing power. In the most basic form of zSense, we use one infrared sensor and 2 emitters, and we can track up to 5 distinct finger gestures with 91% accuracy, and it consumes very low power, about 8 milliwatt, which is like 2 orders less than leap motion. And again, the data produced from the system is about 0.2 kilobytes per second, which is again much less compared to camera-based systems. And we use off-the-shelf infrared sensors and emitters, which is few cents. The cost is about few cents. How do we do it? We use a new method called Non-linear Spatial Sampling. Rather than illuminating the whole space, we illuminate different areas of the space differently, which is called spatial light modulation, like this. And we do it really fast. This also reduces the energy required because the illuminators are not on all the time. If I further simplify it, imagine a target in front of a sensor like this and with 2 emitters. Traditionally, we can capture one variable from this sensor. But in zSense, we turn on and off these emitters in different manners, so we can expand these variables to 4 using just one sensor. Interestingly, we found that these 4 variables actually embed information about the location of the target. Then we, of course, went into mathematics and modeled it to find out how this information are actually embedded, and we found how it is related to the pattern and the location of the target. But I'm not going into a lot of mathematics simply because I want the audience to be awake during the rest of the talk. So let's come back to the simple way that we have 4 variables which has somehow embedded the location information. Then we feed them into 2 stages of machine learning classification stage. First stage, we don't have to train for each user, which simply extract the location information. And this location information is feed into a base network, which has to be trained per user because different users perform gestures differently. And gestures come out. The interesting aspect of zSense is its spatiality. So we achieve this through relatively displacing sensors and emitters like this. Here, the variable E is the displacement, which makes all the difference in the system. So we can leverage on this when we go into applications and implementation. For example, 3 sensors and 3 emitters can be embedded in the edge of a smart glass like this in a linear fashion. Or we can embed 3 sensors and 3 emitters again in either corner, each corner of a smartwatch, making it a triangular configuration. Also, we realize it doesn't necessarily have to be a linear displacement. So imagine a very small device. We don't have space to have the linear displacement. We can simply rotate them. There is an angular displacement. Somehow we have to achieve the spatiality. So this is very useful in something like a ring because it has a naturally curved surface. So we can leverage on this affordance to embed or implement zSense on a ring. Of course, then we went to an evaluation phase. We evaluated the system for all these 3 configurations like linear, triangular, and angular configuration. We set up this small grid mechanism so that we can keep the consistency between users. We had 12 users participating in 3 different sessions, and we used a gesture pool that consists of static poses like 1 finger, 2 finger, 3 fingers, and also dynamic poses like using 2 fingers you can move the differentiate the pose, and also static pose paths, which is like moving, slide, like sliding, rotating, and so on. We use the classification from Woodbrack and colleagues. They did a classification of gestures. In results, we found in 3 sensors and 3 emitter configuration, in the linear configuration, we can track up to 9 gestures with minimum accuracy of 85%. And in the confusion, we realized there is 1 gesture which is making a lot of noise around. So we removed it, then we could get about 90% accuracy for 8 gestures, just using 3 sensors and 3 emitters. And same in triangular arrangement, we could track 7 gestures with again 91% accuracy. Finally, in just using 1 sensor and 2 emitters, we could track 5 distinct gestures again with 91% accuracy. So what is the application of this kind of technology? Since it needs very little space and little energy and very little processing power, this is ideal for always available gesture input. So someone can wear it throughout the day, and you can just answer a phone call or change your music track in your iPod using a flick of a finger. But we are also interested in other application domains such as medical rehabilitation. Imagine a patient who is in rehabilitation for his finger, how his finger moves, so we can track their finger motion throughout the day. Also, we like to use it in other fun applications, like to play a game on the go in your mobile phone, or using Google Glass or something to interact very easily rather than moving around your hand to your head. So this is me playing a game. This is actually I'm playing using zSense. So I think it's quite fun. Anyway, it is a work in progress, so there are limitations. First of all, this is meant for smaller devices. The range of zSense is about 15 centimeters, which is very small compared to Leap Motion or Kinect. But in the application domain we are interested in, I think this is good enough. And also it has inherent limitations due to using IR. For example, if we want to use it under direct sunlight, then the performance will be really diminished. What we are working on right now as future work is to improve the location accuracy. Even though this system works very well for gestures because it's a collective of locations, but as a pointing device, it is quite bumpy. You can see 3 gestures performed by a user. This is a circular gesture, how the location is bumping around. This is partially due to the user error because we are not really good at pointing or making consistent gestures in such a small scale. But again, it's there is a lot of contribution from system as well. So we are now working on how to improve the location accuracy of the system. In conclusion, we introduced zSense, which uses a non-linear spatial sampling scheme to implement implement gesture tracking for spatially constrained devices with very little power consumption and very little processing requirements. Thank you very much. I will answer any questions.
Hi, Paul from Postec. You suggested 5 to 9 like gestures to classify, and then the performance showed quite a good performance. And then, but I doubt like within the class space, the performance was good, but considering the characteristics and the property of the wearables, there may be a lot of noisy inputs. Then it is also important to distinguish the noise and the real gestures. So have you considered about that?
Because we use the different illumination patterns, there is a stage where all the emitters are turned off. So this captures the background noise. So this is also one of the factors feed into the classification stage.
I mean, like something stick coming, like I'm passing something like behind me, like there is a stick.
True.
Like
you mean like non-intentional input?
Yeah. That's what I mean.
Yeah, that's that is actually a valid point. Yeah, we right now we don't have special way to eliminate this kind of unintentional input. But I think this is valid for almost all the interfaces we use, even our mobile phones, touch screens. There is a special mechanism to activate the input system itself. I think we can use something similar. You know, when you want to activate it, you turn it on.
Okay, thank you.
Thank you.